Hello, AP Chemistry, and welcome to the final part of Chapter 5, Standard Heats of Formation, right? Symbolized as delta HF naught, right? Naught, right? The little degree sign, right? Meaning standard, at standard conditions, under standard conditions, which is about room temperature, about 1 atmosphere, right? And things being in their standard states for that temperature, okay? I put a list in your guys' outlines for standard states that you need to know from memory. So make sure you review those, okay? And the F stands for formation, meaning to form 1 mole of said thing. So let's practice writing some standard heats of formation equations, okay? Let's say we want to write the standard heat of formation for H2, for gaseous H2, which is the standard state at room temperature. Right, ta-da! This is a trick question, not a trick question, a thoughtful question. In that, this would be 0, right? There's no heat of formation reaction for that, or equation, because it is already that thing, right? There is nothing that is done to make H2 be H2 gas at room temperature. So, let's do this one, CO gas. So if we want to form CO gas, and specifically 1 mole of it, because that's what the definition of heat of formation is, right? We would have to start with carbon in its standard state, right, which would be solid graphite, plus O2, because O2 is elemental oxygen. And then what do we have to do? Right, put a 1/2 here. We don't often use fractional coefficients because that doesn't make sense, right? We're not going to have a half of an O2 hanging out. But we have to have definitions for things, and the definition for standard heat of formation is to form 1 mole of product, which means that, yes, we are going to have fractional coefficients, okay? Now for CCl4, that one's a little bit easier. Right, we're going to start with carbon in the form of graphite. And then, excuse me, we're going to have Cl2. Specifically, we're going to have 2 Cl2s. Yes? All right. H2O means we're going to have H2. We're going to have O2. And then what? Right. Another 1/2. Yes? All right. That's how we write standard heats of formation equation. Now, if we want to use heats of formation, right, one, we have to think back to the beginning of the chapter where change, right, is always going to be final minus initial, right? That's what change is defined as. So if we want to do our standard heats of formation, basically we're going to take the sum of these minus the sum of these, yes? And then we're going to subtract them, right? As in this is the sum of these is how much energy the products either release or absorb, right, versus how much is released or absorbed here, okay? And these coefficients matter, all right? So let's go ahead. Let's say we're given this table, right? You wouldn't have to memorize any of these, right? But we have CO2. So let's go find CO2. Now, the only trick here is that some of you guys, because you're going to have to use the table in the back of every book and the table on WebAssign, if you're not paying attention, you might just jot down the wrong thing because the phases also matter, right? If something is a liquid, gas, or a solid, that matters, right? Because that has a different heat associated with it, right? And you'll see here, right, so for example, water has a certain heat, right? Liquid water versus gaseous water. So it's really, really important that you pay attention. So here we have, what am I doing? CO2 gas. So here is our CO2 gas at negative 393. So negative 393.5. And note that this is kilojoules per mole, right? Kilojoules per mole of CO2. Okay? It turns out that we have 2 moles of CO2. Okay, and so this is like term 1. We also have 3 moles of water. Times, we would go find water. By the way, this is liquid water. So we'd go find liquid water. Negative 285.8 kilojoules per mole of water, right? And this would be my products. So I would sum these, right? And that would be the heat for my products, and then I would subtract, right, the same thing for my reactants, where I would have 1 mole of this, and I would go find that number 3 moles of that. I would sum those, and then I would do this difference, right? Do remember your order of operations, right? Wherein you'll multiply, multiply, add, right? Multiply, multiply, add, and then we'll do this subtraction step at the last. Yes? Fantastic. And that's how we could find the heat of a reaction using enthalpy or standard heats of formation, okay? Now, because it's just a chemical equation that says, right, your heat of a reaction is equal to the sum of your delta HF products minus the sum of your delta HF reactants, right? That means that since it's an equation, if we know this, which is going to be this piece of information, right, we can plug in all these x's, right? We can go find copper, we can go find water, we can go find H2, and plug in an x for CuO, right, to find that last piece. Yes? Fantastic. All right. Thank you for listening. Be good. Have a wonderful day, and I will see you soon. Bye.